Hi, my name is Braden, and today I'm going to be talking about energy-based models. If you do any amount of research into energy-based models, you'll see pretty quickly that this is a topic Yann LeCun has been one of the major people advocating for quite some time. So I wanted to motivate today's discussion with a couple of quotes from Yann. So he says, probabilistic modeling comes with a high price and should be avoided when the application does not require it. And he also says, in good humor, maximum likelihood sucks. So today we're going to dive into where these opinions come from and what Yann means when he says these things. So components of an energy-based model. So there's four things we're going to have to cover. The first is the architecture, which is the parameterized structure of the energy function. This is really just our model. And we're not going to put any constraints on how we parameterize this function. So right off the bat, you can be thinking of energy functions as being a complicated neural network. We're going to represent F as our energy function. So F is our neural network, and it's parameterized by W. So W would be the weights of the network. X is going to be a set of observed variables we're going to provide as inputs to the network. And Y will be a set of unobserved variables that we're going to have to solve for during inference. In this expression, this F of XY is called the conditional energy-based model formulation. I just want to quickly note that there is an unconditional version where you would basically just remove the X and have F of Y. And that would allow you to take an energy-based perspective on many unsupervised learning algorithms like K-means and PCA, but that's not something that we're going to dive into today. Next, we have our inference algorithm. And this is kind of a mental hurdle to get past when you start looking at energy-based models. And that's that no longer do we have a deterministic function where we provide an input and get an output. Now, prediction time requires an optimization procedure. And the best inference procedure is going to depend on the type of unobserved variable. So if, as I'm going to assume in this talk, if Y is continuous and our energy function is smooth and well-behaved, with respect to Y, then gradient-based methods such as conjugate gradients could be an appropriate inference procedure. But of course, if Y was discrete, we would have other tools we would need to use. Third, we have our loss function, which is just our way of, during training, measuring the suitability of our energy function on the training set. And then, of course, we have our learning algorithm, which is going to be our method to actually find the parameters W that result in our energy function being useful. Okay, so taking a closer look at what an energy function is, I want you to think about an energy function as being an implicit function that captures the dependency between X and Y. So this will be, in contrast to an explicit function, which would a deterministic neural network would be, which would compute Y given X. Now we're going to try to just model the dependencies of X and Y. So in this first row of images, the black beads represent our manifold of data. And so the job of the learning algorithm of training is going to be to bend this energy surface in such a way that we're giving low energy to things that are close to the manifold of data. So giving low energy to the stuff we care about and higher energy to everything else. And we're gonna pick a loss function that's gonna help us do that. There's two broad categories of methods for training energy-based models. The first is a contrastive method where you're going to actively find the correct answer. So find points that are on the manifold of data, and you're going to pull the energy of those points down. And then you're also going to have to find contrastive examples. So wrong answers, and actively push the energy of those points up. And there's tons of papers and research on ways to make this work well. Most of it focuses on smart ways to pick those contrastive examples, because oftentimes there's tons of wrong answers. And so you have to kind of be intelligent about which points you're pushing up, because you can't push up on everything. But that's really one of the drawbacks of these contrastive approaches, that you have to find those points that you're going to actively push up. Another method is called regularized or architectural methods, where you don't actually push up on anything. All we're going to do is pull down on the correct answer, but we're also going to have some sort of way to limit the amount of space that's allowed to take low energy. And that way, when we pull down on the correct answer, we effectively are pushing up the energy of everything else. So at inference time now, we're going to be looking for Y check. It's Y check because it has that kind of downward V to it. So we're minimizing. So we're going to look for Y that minimizes our energy with respect to the X that we've been given. And so looking at these energy services up top, we're going to imagine being given an X and then have to use our inference procedure to kind of traverse across our energy function to find the value of Y that results in the lowest energy. And that's going to end up being our prediction. And so since this is an optimization procedure, there could be multiple solutions, meaning there are multiple low energy Ys that are kind of at equivalent low energy states and correspond to the same input. And that's completely valid in this framework. And looking at cases of underfitting versus overfitting. So on the far left here, we have this flat plane as our energy service. And this is underfitting because we haven't really modeled anything, right? There's no dependency between X and Y that's taken shape. And our inference procedure really wouldn't work at all because if we're trying to follow gradients to a low energy state, we have no gradients to follow at all. It's just completely flat. On the other side of the spectrum, our overfitting case, we see this one on the far right where we have everything outside of the manifold of data is at high energy. So we have this deep, steep canyon where you can barely see the manifold of data at the bottom. And then everything that's directly outside of that has been pushed up to high energy. And this is bad for a couple of reasons. I mean, one, our inference procedure is going to have a heck of a time even finding this canyon, right? So given an X, are we even going to have gradients in this high energy desert up top that even lead us to the canyon? And second, is this even a reasonable way to model the dependency between X and Y? I'd say in most cases, probably not, where one step outside of the manifold of data, you wouldn't expect the energy to shoot up drastically. You'd expect something more like you see in the middle where, close to the data, you get low energy. And then as you move further and further away, you get this smooth transition, which is also going to be very conducive to our inference procedure. Okay, so now I want to introduce the Gibbs-Boltzmann distribution, and it's going to draw a connection between our energy-based models and familiar probabilistic approaches. So Gibbs-Boltzmann is one method to take any set of numbers and turn them into something that looks like a valid probability distribution, meaning that all numbers are between 0 and 1 and that they sum to 1. And so in this equation here, we have our F, our energy function. So this would be the output of our neural network. And we're taking e to the negative beta times that value, where beta is just some positive constant, and it's akin to an inverse temperature in physics. In general, the value of beta is not super important, but it will affect the smoothness of our probability distribution. So depending on the value of beta, you may end up with a situation where almost all probabilities are very close to 0 and only the one correct answer is high, or you could end up with something with a little bit smoother where you have a set of probabilities where many of them are not 0, but they're somewhere in between. Down here in the denominator of this, we have what's called the partition function, but really it's just a normalization constant. And this is important because it's really kind of at the heart of why Yann LeCun says probabilistic modeling comes with high costs. Because looking at this closer, we see this is an integral over y prime. So it's an integral over the set of all possible outputs. Now, in many interesting and useful cases, you won't be able to compute this integral directly. If y is something that's high dimensional and continuous, like an image, you can't integrate over the set of all possible images. And so you're going to have to come up with some sort of Monte Carlo method or sampling approach or some sort of trick to even compute this integral. And so in that situation, the argument would go that, if you can't compute the integral and you're having to resort to some trick to even get your normalization constant, do you really need probabilities that bad anyways? Or could you just use the energies directly? And tying this back to a familiar example of a Gibbs-Boltzmann distribution for the discrete case is just the softmax distribution, which we see here. The integral has been converted to a sum, and we're all familiar with this at the output of our classification neural networks. So now I'm going to make the claim that probabilistic models that learn the conditional distribution that we looked at on the previous slide, the conditional distribution of y given x, are really just special cases of energy-based models that meet a set of two conditions. So the first is that partition function, that normalization constant, is something that we can compute. And the second is just that we've trained with maximum likelihood. So we're using the negative log likelihood loss. And over the next several slides here, we're going to start off with the maximum likelihood objective, and we're going to show how the maximum likelihood objective kind of implies the negative log likelihood loss, and how when you use that to train your energy-based model, how that objective causes the energy function to take shape. So here we're in the classification setting where we have our data set S, which is made up of XY pairs, inputs, and the associated label. And we have our probabilistic hats on. So we want to train with maximum likelihood. We say, I want to find W, the parameters of my neural network, that result in the maximum probability of all my targets given all of my inputs. I want to find the parameters that do that. And say, okay, well, how do we calculate that? So right off the bat, we have to make an assumption, and that's that all of our samples in our data set are IID. And if we make that assumption, then we can turn this calculation into the product of all the individual probabilities for the XI, YI pairs in the data set. And that's just because if you have a bunch of independent things all occurring together, it's just the product of their individual probabilities. So we get to this expression and we say, well, that's not going to be numerically stable, right? Because we have a bunch of numbers between 0 and 1. We're going to multiply them together. Could have some underflow problems. So why don't we take the log of those probabilities, which will let us turn our product into a sum. Okay, great. And now say, well, okay, well, remember W is the parameters of a neural network. And I'd really like to train that neural network using some kind of gradient descent. And so why don't I just add a negative sign out front? That'll take my maximization problem, turn it into a minimization problem. And lo and behold, we've arrived at something that should look very familiar, our negative log likelihood loss, also called cross entropy. It was a very familiar loss in probabilistic modeling. And for this next step, we're going to have to recall that, okay, this conditional probability of y given x can be found from our energy-based model using Gibbs-Boltzmann. So if we take the expression for Gibbs-Boltzmann and we plug it in, each term in that sum looks like something at the bottom of the screen here. We have negative log of this fraction. Okay, so then we can recall that we have the log of a fraction can be rewritten as the log of the numerator minus the log of the denominator. And inspecting this, we see that log and log will cancel. We have some minus signs that'll cancel. So we can clean this up a bit. If we go through and divide by beta, we end up with this loss for a single sample, which is made up of two terms. So the loss for xi, yi is related to the energy of the correct answer and this second term, which physicists call the free energy, which is basically related to all of the answers, correct and incorrect. And so now, if we're actually going to want to train our model with this loss, we're going to have to take the gradient with respect to the model's parameters. So taking the gradient of this loss, this first term is pretty trivial, right? It's just the gradient of the energy of the correct answer. But the second term is a composition of functions. So we're going to focus on that for a little bit. We have to apply the derivative of a log is 1 over x and the chain rule. Again, we have another application of the chain rule with this exponential here. And we see that the gradient of the second term is starting to look scary, but something beautiful happens. And this equation for Gibbs-Boltzmann kind of reemerges. And so this second term really becomes a probability that our model assigns to a point multiplied by the gradient of the energy at that point. Okay, so what this second term really is intuitively is kind of turning into an expectation or a weighted sum where we're weighting the gradient at each point by the probability our model gave to that answer. So let's take a look at what happens when you actually use this gradient to update your parameters. And so this part is worth pausing and really thinking about for a minute, because this is exactly why Yann LeCun says maximum likelihood sucks. So we're going to have to remember the gradient points uphill. So at the bottom of the screen here, we're taking our parameters W and we're updating them by subtracting some learning rate multiplied by the gradient of the energy at the correct answer. So we're going minus the gradient, so we're going downhill. And so we see that this first term is doing exactly what we want it to do. It's pulling down the energy of the correct answer, which is great. I mean, that's how we want our energy surface to be shaped. But what's the second term doing? Well, we see that there's a plus, so we're going in the direction of the gradient. So things are being pushed up by this term. And what's being pushed up? Well, we're integrating over all of the answers. So everything is being pushed up by this term, including the correct answer. So it's important to pause and keep that in mind too. Even the right answer is being pushed up by this term. It's just not being pushed up as hard as it's being pulled down by the first term, right? So all points get pushed up by this second term, and they get pushed up by an amount that's proportional to the probability our model gave to that point. So remember, low energy is good. And so low energy is like high probability. So if our model gave high probability to an answer, it's the wrong answer, it's going to push up that point very hard, right? But if the probability was already low, it'll be a smaller weight on this gradient. It won't be pushed up as hard. And so this is actually undesirable for energy-based learning in the sense that it's building exactly that overfitting case that we looked at a few slides back, right? Where if maximum likelihood has its way, it's going to do as the name implies, it's going to maximize the likelihood of the data that was observed. So the only thing that's going to get pulled down harder than it gets pushed up is the points that are on the manifold of data. Everything else is going to get shoved up. And, you know, in the limit of training that way, you're going to end up with this overfit looking surface where anything just outside of the manifold of data is going to have its energy pushed up, which is not going to be very conducive to our learning procedures. This was a really cool insight for me. So I think it's worth kind of maybe taking the extra time to read these boxes and think about what's happening there. And so I just want to leave you with one final thought of why do we use energy-based learning? And there's at least 4 good reasons, I'd say. The first should probably be obvious by now, is that we don't have to deal with potentially intractable integrals to estimate normalization constants. The second requires us to think a little bit about what is the job of the model, right? And if your goal is to make decisions, you could argue that probabilities really aren't that useful anyways. Take, for example, a self-driving car. If a model outputs that you should turn left with probability 0.8, you're going to turn left every single time. So what was that 0.8 really doing anyways? Just as effective would have been an energy-based model that gave the lowest energy to the correct answer and told you to turn left. It's the same result. Number 3 is something that I really wish I would have been able to dive more into in this discussion, but if you do go take a look at the references I'm going to share here in a minute, there's tons of discussion on alternate loss functions, because as soon as you decide you don't need probabilities anymore, that means you don't need the negative log likelihood loss, which opens the door to tons more loss functions that could be useful, potentially more useful in crafting an energy surface to model our dependencies. And the last is also something I really wish I would have been able to cover in more detail, but it's this concept of there are circumstances where it may be valid to give multiple correct answers to one input. A common example that Yann likes to talk about is video prediction. So if you're building a video compression system and you need to be able to predict the next frame, or there could be multiple next frames that are valid for a given current frame, right? And so you need a way to tell the system that there's multiple correct outputs. And there's extensive discussion on use of latent variables, where you can take, say, an extra variable z and vary that over some set to change the output given a constant input. Lots of discussion on that in the references. So yeah, the most useful reference to me was this paper from Yann LeCun in 2006. He called it a tutorial on energy-based learning. It's a little bit long as far as papers go. It's about 60 pages, but well worth the read. Also, Yann runs a deep learning course at NYU, and all the videos are free on YouTube. And there's a couple websites that go along with it with awesome resources that are all for free. Definitely worth checking out. As far as books go, it's actually pretty difficult to find books on energy-based modeling. I know actually Yann's team is working on writing one, but one I did find useful for this was called Deep Generative Modeling, where chapter 6 is all about EBMs. So with that, that's all I have. Thanks for listening, and I hope you enjoyed the talk.